Okay, so topic 3, fluids. Again, can you tell me what is fluids? What is fluids? It's a substance that can flow, correct? So, it can be either gas or liquids. So in terms of describing the properties of fluids, two terms are being used. The first one is the density, which denoted by the symbol rho, and is calculated by mass over the volume. So the SI unit will be in kg over meter cube. Another property to describe fluids will be the pressure. So pressure denoted by the symbol P and is calculated by force in Newton over the contact area. In the unit of meter square. So there are two types of pressure which you have learned in your semester 1. The first one, the gauge pressure, given by rho GH. So G is the gravity acceleration, 9.8 meter per second square. H is the depth, so in the unit of meter. Absolute pressure is the actual pressure at that particular point. So for absolute pressure, you must include atmospheric pressure in your calculation. Okay, so the difference between the gauge pressure and the absolute pressure is, for gauge pressure, it is exclusive of atmospheric pressure. However, for gauge pressure, then you have to include your atmospheric pressure. That's all. Alright? So 3 principles related with fluids. The first one is Pascal principle. So Pascal principle say that if you have an enclosed incompressible fluid. So what do you understand by this incompressible fluids? It only subjected to liquid now. Huh? Gas is compressible fluids. So Pascal principle does not apply to gas, but only incompressible fluids like liquid. Okay, so when you have an enclosed incompressible fluids, for example, like a hydraulic jet, let's say. So any pressure that you apply on one point here will be transmitted equally to every portion inside this enclosed incompressible fluids. Okay, if you apply a pressure of P here or P1 here, so at every point, every portion here in this container, they will be receiving the same amount of pressure as P1. Alright? So if you put here as, okay, PA, and if you put here as PV, so we can say that PA is equals to PV, which is equals to P1. So by expanding the equation, we have already known that pressure is given by force over area. So force at point A over the area at point A will be equals to FB over the AB. Right? So we can say that F over A at one point, that being applied at one point, is constant at any point inside that enclosed container which contain incompressible fluids. Okay, so that is about Pascal principle. The second principle is Archimedes principle. So Archimedes principle talks about buoyant force. So when an object is submerged in a fluid, so in this fluid can be both gas or liquids now. Okay, so when an object is being submerged, either partially or fully, there will be an upward force. So remember, buoyant force is always an upward force. It's always going up. Okay, so there will be an upward force applied on the object. So just a top up of what you have learned in your free body diagram. So usually when we have an object, a substance with a mass, then definitely we will have our weight, right? Weight equals to mg. Okay, so what a new force that has been added in here is whenever the object is existing in a fluid. Okay, fluids either gas or what else, liquid. So there will be an upward force, which is the buoyant force. That's all. Okay, so whenever you solve the question, just remember the first step that you have to do is to draw the free body diagram, and it will be easier for you to solve. Okay, so how to calculate the buoyant force? This one super very important. Buoyant force is calculated by this. Okay, buoyant force is equals to the weight of the liquid displaced or weight of the fluid displaced by the object. So is equals to mass of the fluid displaced times g, or when you further expand it, it's equals to rho Vg. So this rho is the density of water, and V here is the volume displaced. Okay, density of fluids. This is the volume of fluid displaced, and G is the gravity acceleration. Okay, so if the maximum buoyant force, when I mention about maximum buoyant force, means when you submerge everything, submerge the whole things inside the water, yeah? When, okay. Okay, so when you submerge everything inside the water, so this is the maximum buoyant force, okay? So when this maximum buoyant force, no sound? Hello, can others reply if you can hear me? Oh, did you turn on your speaker? Yeah, did you turn on your speaker? Perhaps you forgot to turn on your speaker. Okay, so that will be your maximum buoyant force here. So if the maximum buoyant force is larger than the weight of the object, then the net force will go upwards. Yeah, okay, so the net force will go upwards, then it will cause the object to float on top of the water. Okay, so if your buoyant force, the maximum buoyant force, is smaller than the the weight of the object, then there is a net force which is going downwards, and eventually the object will sink down to the bottom. So if the maximum buoyant force is just equals to the weight of the object, then there is no net force acting on the object, so the object will suspend. So it is just like if you, okay, let's say if you, this is your hand, if you push the object down here and you release, okay, release, and I erase the hand, then the object will just stay there without moving anywhere. Alright, so this is how the submarines work. Okay, they can choose. So let's say if they want to go to somewhere which is shallower, then they will release more water. So the water will be replaced by air. Then the submarine, the weight of the submarine will become lighter and they can go up a bit. So if they want to go down to the bottom a bit, so they will suck in more water, so to make the weight become heavier and they can go down. Okay, so that is how the submarine work by applying the Archimedes principle. So I would like you to try on this question, or we try together. Yeah, so a scuba diver with her gear, so displays a total volume of 65 liter, and the total mass is 68 kg. What is the buoyant force on the diver in the sea? So diver, right? So definitely, literally means the whole person will be underneath the water. Okay, so this is the gear and this is the diver. Okay, so the volume here, this will be the volume displaced, which is equals to 65 liter. So to find the buoyant force, rho Vg, rho of the fluids or the liquids, V volume that displays, G is the gravity acceleration. The density of the seawater is 1.025 times 10 to the power of 3. The volume displaced 65 liter. Convert to SI unit, times 10 to the power of, anyone? Negative 3, yeah? Convert to SI, yes, very good. Convert to SI unit to meter cube. G 9.8. So find left. How much? You get 653 Newton. So this is the total buoyant force acts on the diver. Okay, so let's draw the free body diagram. There will be an upward force which is equals to buoyant force, and also a downward force which is equivalent to the weight of the diver. Okay, now will the diver sink or float? So to find the downward force, equals to mg. The mass given here is 68 kg times 9.8. So you get a downward force of 666 Newton. So will the diver sink or float? It will sink, right? Because your downward force, since downward force is larger than the upward force, then the diver will sink down to the water. Alright? So which is actually work. I'm not sure whether have you dived before, but last time when I joined a diving course, the coach actually told me not to eat too much, because when you get if you eat more and you get bigger in size, you displace more water. So when you displace more water, even though you are heavier, but somehow when you displace more water, the buoyant force that acting on you is higher. That's why it's difficult for you to sink down to the water. It's easy for everyone when we go to diving. It's easy for us to float. Why? Because if you want to float, you can just pump in more air into your into the diving suit. Then it's easier for you to float, but it's very difficult for you to sink. So that's why this is the advice that given by the coach. Do not eat until you expand your size, because if the size is very big, then you displace more water. So again, the Archimedes principle is applied here. Alright. So next move on to the Bernoulli principle. So before we move on to Bernoulli principle, there is one very important formula here. We call it as equation of continuity. Okay, so it means the volume flow rate. Okay, it's talk about the volume flow rate. So volume flow rate at any point of the moving fluids, it's always the same. Okay, it's always constant. So volume flow rate is actually given by, so if you learn in your degree, usually the symbol given is Q naught. So it's always given by volume divided by time, and the unit will be meter cube over seconds. So when you further expand, you can get A times V, where your A is the area, cross-sectional area, and this small capital B is the velocity of the fluids. So all this is for the dynamic fluids. Dynamic fluids means when the fluids is moving. Yeah. So follow from this equation, the main equations for Bernoulli is this long and complicated one. Okay. So P is the absolute pressure in the unit of Pascal, plus half rho V1 square. Rho, again, the density. V is the velocity. Plus rho Gy, okay. G is the gravity acceleration, which is 9.8. Y1 is the elevation. In meter. Okay, so the whole expression here, it's constant at any point. So let's say this is your pipe here. The size of the pipe will change to a bigger size, or even the height will also change. No matter how does the size of the pipe or the position of the pipe has changed, your expression, okay, I mean this expression, P plus half rho V square plus rho Gy will be constant inside the pipe, right? So this is what it means by Bernoulli equation. So any question about all the principle? If no, then let's try on this question. for the application of Bernoulli principle. So water at a gauge pressure of 3.8 atm at street level, so flows into an office building at a speed of this through a pipe of 5 centimeter in diameter. Okay, so we can draw the diagram for this one. So I draw here. So this is your building. No sound again. How about others? Can you hear me? Then perhaps you have to check your speaker, huh? Okay, you check your speaker or you check the setting in your WebEx. The selection of your speaker. Alright. So if this is your building and we have a pipe here. From the street level to the, you don't have sound also. How about others? Or perhaps you can check your video. You go to setting of your video. Sorry, you go to setting. Wait, where can you find? Check audio and video. There is a setting, and perhaps you can check what is the output of your speaker, because sometimes what happens is when we accidentally connect to other speaker like Bluetooth speaker or perhaps your headphone, sometimes it does not change back to the original setting. Okay, so we have a pipe from street level to the top of the building. Okay, so let's label the two positions. So if I met the first position is on the street and the second position is on the top floor. So list down the information that you have. At point 1, given the gauge pressure is 3.8 atm. Convert to SI unit, to Pascal. Do you know how to convert? So 3.8 times 1.01 times 10 to the power of 5 Pascal. So speed V1 is 0.6 meter per second. The diameter through a pipe, okay, diameter, so D1 is 5 centimeter. And at point 2, so the pipe taper down to 2.6, which means your diameter 2 is equals to 2.6 centimeter. So it is 18 centimeter heights in different relative to the street. So if y1 equals to 0, then y2 will be 18 meters. Can, Or can you try, or perhaps you try to connect with headphone? Or perhaps Another thing is sometimes if you do not update to the latest version, there might be some miscoordination in the WebEx. So you go out and check, is there any updates that you can do? Yeah, you cannot hear me. Someone, can you help to type this in the chat so that your friend can see if there is any updates needed for WebEx? Then you also need to install. Yeah. Oh, thank you. Okay, so calculate what you have to calculate at point 2 is V2 and also the gauge pressure 2. Okay, so I will open a new file here to solve this question. Okay, so from here, in order to find the velocity at point 2, we have to use the equation of continuity, right? A1 V1 equals to A2 V2. Wow, the color change. Okay, so the area in position 1 is pi r square, right? So you are given with diameter, convert diameter to radius. 5 centimeter SI unit 0.05 divided by 2 square times V1, which is 0.6, equals to pi. Diameter 2 is 2.6, so convert to meter 0.026 times V2. So your velocity is 2.2 meter per second. So find the gauge pressure at point 2. Okay, so from Bernoulli equation, P1 plus half rho V1 square plus rho GY1 equals to P2 plus half rho V2 square plus rho GY2. Remember, yeah, this one must be absolute pressure. So absolute pressure 3.8 times 1.01 times 10 to the power of 5 plus, this is gauge pressure, plus atmospheric pressure. Okay, this is only the gauge pressure and this is your atmospheric pressure. Density 1000, no? Velocity 0.6 square plus density 1000, 9.8. Okay, y1, it's your reference point, which is 0. Or the browser. How about checking the setting there? Okay, P2 is what you have found just now. Yeah, thank you. Thank you, Fu. So Y2 is 18. Okay, so from here you can find the value of the P2. So what is the answer of your P2? Around 306160 Pascal. So that is absolute pressure. To find the gauge, you have to minus 1.01 times 10 to the power of 5. And you get 2.05 times 10 to the power of 5 Pascal. Convert back to ATM, you get around 2.0 ATM. Okay, so that is your gauge pressure at point 2. Okay. Are you okay with all the principle for fluids? Yes. Okay, so let's move on to the tutorial worksheet. We will complete our first section, pressure and Pascal principle, before we have our 5 minutes or 10 minutes break. So what are the total force and the absolute pressure on the bottom of a swimming pool? Okay, you have a swimming pool. The dimension of swimming pool, okay, 22 meter times 8.5 meter with a depth of 2. So what is the total force and absolute pressure at the bottom? So what is the force here and also absolute pressure? So to find the absolute pressure first is equals to atmospheric pressure plus the gauge pressure, right? Atmospheric is 1.01 times 10 to the power of 5. So gauge pressure given by rho GH, remember? So 1000 times 9.8. So H is the depth, which is 2.0. So you get 1.2 times 1.21 times 10 to the power of 5 Pascal. So what is the force? Okay, from pressure equals to force over air, so force equals to pressure times area. So your absolute pressure is 1.21 times 10 to the power of 5. Area is this is the area. Okay, the dotted line. So this part is the total area. So is that 0.5 times 22? So it's around 2.3, huh? 2.3 times 10 to the power of 7 Newton. So B, what will be the pressure against the side of the pool near the bottom? So just now it's right away to the bottom. How about the pressure on the side here, this one, here on this side, the side here? So it will be the same as the bottom also. Okay, the absolute pressure, yes, very good, is still equals to 1.21 times 10 to the power of 5 Pascal. Why? Because of Pascal principle. Alright, so the amount of the pressure that apply on the bottom, on the side which is near the bottom, okay, let's say this is the swimming pool, huh? Okay, on this bottom here, the one that I color in purple color, okay, this is your swimming pool, the structure. Okay, so the purple color here is 1.21 times 10 to the power of 5 Pascal. So the corner here on the side, it is still 1.21 times 10 to the power of 5. Unless it is somewhere here in the middle, then it will be different, huh? Because of the gauge pressure is also different between this point and this point. Okay, but then if it is all at the bottom, it doesn't matter about the direction of the pressure. Okay, it's still the same, right? And the second one is about the hydraulic system. So piston with a cross-sectional area of 21 centimeters. So this can be your Air1. Okay, so an incompressible liquid with a force of 38 Newton. So that will be your F1. So on the other end, you have an area of 100 centimeters square. So what is the force? So from Pascal principle, F1 A1 equals to F2 A2. 38 over A1, which is 21 centimeter. Okay, so you can remain it as in centimeter square, or if you want to convert to SI unit also can. Okay, F2 is unknown over 100, and you get 181 Newton. Alright, so for this case, you can remain in centimeter square. Okay, why? Because if you double check the unit on both sides, this one is Newton over centimeter square. On the other side, it is also Newton over centimeter square. So since on both sides your unit is consistent, then you can just remain it as centimeter square, right? But if you are not feeling secure, I mean, like some of you might feel insecure, right? What you can do is, yes, you can convert to SI unit, and at the end you will still get the same answer. So 21 centimeter square convert to SI unit will be times 10 to the power of -4. This one is when you convert to meter square. And at the end, check with your calculator, you will get 181 also. Okay? So perhaps I give you a rest for 5 minutes. We come back at 1:55. 5 minutes. 10 minutes. Come back at 1:55. Right? And who are the one that cannot hear the sound? I guess can ask him to install the, is he still here? Yeah, I can type. Did I send out the message? Oh. Okay. So if you have a question, you can ask now. Otherwise, you can go and have a walk and eat something, yeah? Because on the practical session letter, I need you to have some energy. Otherwise, you might pass out. Okay? So eat something, drink something, and go to washroom. So we will come back again at 1:55, right? You mean this one, is it? Okay. Hey, has everyone come back here? Give what? Raise your hand, huh? If you have come back here. Okay, so I would like to share. So, can you all see the setup? Can you all see the setup of four objects on the table? We have one eraser, one Eclipse container, and one cylinder container, and one bucket of water. Right, so what I want you all to do here is, okay, these are the mass of each object. Okay, eraser is 6 gram. Can you see the candle? Okay, it's 6 gram. Eclipse container is an empty one. Okay, I finished all during MCO, so you can guess how heavy I am now. Okay, so the Eclipse container only around 20 gram, and this is the cylinder container empty. It's also empty inside. Okay, and it's 40 gram. So if I put them into the water, so can you predict which one will sink to the bottom? So I will open the poll and you'll vote. Okay, you have 5 minutes to vote. Okay, so based on your first sight, okay, your first observation, and you tell me which one will sink down to the bottom.
Hello, Miss.
Yes?
May I just ask, what is an eclipse exactly? It's kind of like a container.
Which one? Which container?
Like the eclipse. Is it a container or
Is the
is it just
container. The total mass of the whole container is 20 gram. This one made of steel. You see, you can hear the sound.
Alright.
This is a plastic container and it's the heaviest among all.
Alright, thank you.
So let's see your prediction. Or we call it as the sense of engineer. On the first look, okay, you can predict. When I was in my degree, my lecturer told me that you all are future engineers, so you have to train your sense of engineer. What do I mean by sense of engineer? Let's say if you look at the container, immediately you can tell, oh, what is the size? This one, you look at the pipe and then you can call out the size of the pipe. And you look at the length and immediately you can predict, oh, what is the length? So he said that is the sense of engineer, which I find it very difficult. So are you all done? We still have 15, huh? 15 not yet started. 14. Okay, so I guess majority of you have already answered, and we have 21. Okay, around 50%. Only eraser will sink down to the bottom, and we have quite a few mentioning about eraser and cylinder that might sink down to the bottom. Wow, everyone so support. Everyone is a support fans of Eclipse. The Eclipse will never sink down to the bottom. Okay, so now I guess most of you, you have quite good sense of engineer, yeah? But now we have to verify. So as an engineer, not only we predict and we do calculation, but we also verify whether our calculation is correct or not. So now comes to the time of verification. Which one do you want me to throw into the water first? Drop into the water first.
Eraser.
Don't want now. So many of you choose eraser. We put this one at last, right? Can? So
The Eclipse.
Eclipse lah. Okay, so the first, everyone is a support of this one. They think it will not sink. So let's see. On the mass of 20 grams, so when I drop them into, it didn't sink. So your sense of engineer is right, is correct. Okay, so Eclipse doesn't sink. How about this one? Okay, this one is a lot of people argue about this one, right? Because it's the heaviest among all. Okay, so let's see. Okay, 3, 2, 1. Oh, didn't sink also. It's still floating. So now, let's look at the eraser. Boom. Yes. Okay, can you see? It actually sinks straight away down to the bottom, even though it is the lightest. Okay, so what can you conclude from this simple demonstration? No, cannot see. Okay. And then I move nearer to the camera. See? We need to include the air in the box. Okay, the air.
I think like space or like the composition
Yeah.
of the material.
So this is the surface of the water, but your eraser is down at the bottom. Okay, so eraser cannot survive the floating. Only see the paper. Which paper? This paper, How eraser here. Here. This is the eraser. Okay. So, anyone can draw a conclusion for this demonstration? What can you conclude from this demonstration? Mass is not everything. So, if you are heavy, don't be too sad because mass is not everything. Right? Anyone? No conclusion.
Is it in my like perspective?
Sorry, can you repeat your question?
I know. Like for the conclusion part, it's kind of like my view about it is that, both the Eclipse and the cylinder has hollow spaces. They have like half space in between, so it doesn't really put much of the weight to come down, I guess. So that's why it's kind of like it floats. And like while the eraser, like the composition of the eraser is like the whole thing is like kind of like solid, I guess. And like when it sinks down, the whole weight of it comes down.
Yes. You are somewhere there. So yeah, it's correct. For eraser, it's very concentrated. See, the whole things, your mass is everywhere. Is your eraser is very solid, but as compared to your eclipse, there are some empty space in between, right? And also the container. Okay, but if in terms of engineering ways of explaining, what will you write about the explanation? I mean, like in terms of engineering ways of explanation. Yes, correct. Density. Yeah. So that's why next time, okay, if your friends complain to you, I'm very heavy, tell them mass is not everything. Density that matters. Right? Okay. So for this case, what is the main cause of, even though your cylinder and also eclipse is much heavier as compared to your eraser, however, both of them did not sink down to the bottom. So what is actually taking the main factor of this is because of the density. Okay, so mass is not everything, but density that matters. Yeah. So if you look at this one, okay, so if you compare with the volume, okay, if you compare these three, calculate the density. Yeah. Okay, I need your help to calculate the density for eraser, eclipse, and cylinder. Okay, so perhaps the who are? Okay, or I say all the male student, you calculate the density. Yeah, you calculate the density for eraser. And girls, you calculate the density for eclipse. Girls, we like sweet things, right? So we calculate the density for eclipse. And for those who have already completed, you move on to calculate the density for cylinder. And you type your answer on the chat there. Okay, eraser 1.35, huh? Times 10 to the power of okay, gram per centimeter cube. So in SI unit will be is it? Thousand three, huh? Is this for the eclipse? Or still the eraser? Okay, so around 130 or 1350. Okay, we'll just make it to two, then it's okay, just put it to 3 decimal point. To 3 significance figure. How about eclipse? Do I have girls in the class here? Yeah. Okay. Help me to calculate. Help me to calculate the. Any girls help me to calculate the density for eclipse? 0.57. So convert to SI unit, it's around times 10 to the power of 3. So 570. How much? 570, yeah? Okay. So how about cylinder? The density of cylinder. 216. Okay. So 216. Okay, so if you look at the density, this is the lightest, the second lightest, and the so-called the denser. Okay, so that's why eraser will sink. But however, by looking at the density itself, okay, if you compare to the density of the water, which is 1000 kg per meter cube. So these two, they are lighter than the density of water. That's why they float. But this one is denser than the density of water. That's why the eraser will sink. So what I want to do now is, what I want you all to do now is you all calculate in terms of buoyant force. Okay? And from there, find what is the upward force and find what is the downward force. From there, you predict whether it will sink or float. So I will do for eraser, I will do the eraser for you, and I want you to spend some time to calculate for the eclipse and also the cylinder. So I will be turning off my video, yeah? Okay. So for eraser, so draw your free body diagram. Going downwards will be mg, going upwards will be your buoyant force. So upward force, which is the buoyant force, is equals to rho, density of liquid, times the volume displaced times the gravity acceleration. So the density of liquid given by 1000, volume displaced will be equals to the total volume of the eraser. So 0.33 times 0.009 times 0.015, okay, times with gravity acceleration. So your upward force is 0.436 Newton. Now the downward force, which is equals to weight mg, mass of eraser.
Excuse me, ma'am. Isn't it supposed to be 0.033?
0.033, wait. Yes, correct. Thank you for mentioning out. 0.033. So it will be 0.04, 436. So mass of eraser, convert to SI unit, times 9.8. So 0.0588. So since downward force is larger than the upward force, that's why eraser sinks. Okay, so you do the same for both eclipse and cylinder. Should I? Then you tell me the answer later. switch my position first. Okay, so can you tell me the answer? Wow, thank you. So okay, so for B, eclipse. Okay, so again, draw the free body diagram. So the upward force will be equal to rho Vg 1000 times the volume. So the volume 0.035 times 0.07 times 0.02, and it's 198. Eclipse is 0.343. 0. Somewhere, wait. The upward force, it's around 0. My calculation is around 0.4 something. You get 0.343. Okay, so downward force is the mass, which is times 9.8, and you get around 0.196 Newton, right? So since the upward force is larger than the downward force, so eclipse floats. The third object is the cylinder. So draw your free body diagram. Buoyant force moving upwards, weight downwards. So buoyant force, rho Vg 1000. The volume of the cylinder, pi r squared. 0.02. Which one is 0.025? Oh, you mean... Wait, what did I mention in my... Oh, it's 2.5. Okay. 2.5. Okay, 2.5. Sorry. Okay, it's 0.025. So the volume of cylinder, pi r squared. Diameter is 7.4. So convert to SI unit 0.074. Convert to radius 0.037 squared times the height, which is 0.043. Times 9.8. And the upward force of cylinder is 1.812 Newton. Downward force 40 grams. And you get 0.392 Newton. So the upward force is much larger than the downward force. That's why cylinder floats too. Okay, so that is from the buoyant force. Okay, but in fact, if you look at the sample in the lecture notes, if you can find the density itself, it has already sufficient enough to prove that whether the object will sink or float. Okay, so now move on to the question. So an undersea research chamber is spherical. Okay, so it is round with an external diameter of 5.2 meter. So the mass of the chamber when occupied is 74,400 kg, and it is anchored to the sea bottom by the cable. So start with a diagram. Okay, it's anchored to the sea of the bottom, which means now there is a cable tying to the chamber. So this chamber is spherical. So from here, draw your free body diagram. Under the sea, so there will be buoyant force caused by the sea. So this chamber has a mass. You have the weight, which is going downwards, and what else? It's tied to a chamber, right? So there will be a tension also from the chamber. Okay, find what is the buoyant force. So the buoyant force equals to the weight of the liquid displaced by the chamber. So density of the liquid. So the volume here is the volume displaced times G. So density of the sea water, let's take 1020 as the density of the sea water. What is the volume? So the volume is the volume of this sphere, because the whole thing is now submerged underneath the sea. So the volume of sphere 4/3 pi r square, right? So what is the radius? Diameter given by 5.2. Radius will be 2.6 cube. Okay. So you get 700, okay, 7.34 times 10 to the power of 5 Newton. So that is the buoyant force. What is the tension in the cable? Okay, so this is at this position with all the forces FB with mg and T. Now it is at equilibrium, whereby the net force acting on the chamber now is equals to 0. Okay, so the net force acting on the chamber now is 0. So solved by free body diagrams, treating going up as positive. So FB minus T minus mg equals to 0. FB you found in question A minus T. mg given the mass is 74,000. 400. So you get 4880 Newton. Okay. So that is your tension. Now move on to Bernoulli principle. Any question up to here with the static fluids from Pascal to Archimedes? Can we move on to Bernoulli? Okay. So have you prepared your paper? Everyone, can you show me your paper? You can turn on your camera to show me your paper. Wait, how can I see you all? If you have turned on your camera, I must stop sharing, right? Han, so big your paper. I cannot see me, my webcam. You can only see my back. This is the paper. Can only see the back camera. So big. A very small piece of paper like this will do. Anyone? Okay, so this is my piece of paper. If you want to, a big pepper also can, but later you have to blow very heavily. How about the others? Hello? No one talking to me. So sad. Thank you. Okay, Ken. How about others? Others? Can I see your pepper? Oh, cutting. Can. Okay, so the size of pepper. So for me, I'm making my pepper. Okay, the width is only 5 centimeter, while the length can be longer. Okay, which is around 21 centimeter. How about others? Good. Okay. Show your pepper. Show your pepper. Hi. Are you all asleep already? Can? Yes. That would be good. Huh? Angie, Ashley. Wow, all the A's and B here. You are in the front page. Azim? Yeah, okay, a small piece like this will do. Okay, how about the rest? This is something can? Okay, good, huh? So The length of it's okay. Mine one is 21 centimeter. As long as when you hold on one side here, okay, the other side it will fall down like this. How? I go out a while and I come back to see whether my webcam work or not, because this one is the back camera, it's not the front camera. So while preparing the pepper, so you can follow mine. Mine one is actually the normal A4 pepper. Okay, wait so this is your normal A4 pepper, right? Okay, this is your normal A4 pepper. So what I do is I just cut around 1/5 of the pepper, cut from here. So that will be enough, yeah? So I will log out and log in again, so you'll wet me inside here. Eesh. So Hedges, I will put you as a new host. Later on, you pass the host back to me, yeah? Hello, Hedges. Hello. Okay. Still cannot. It's okay lah. Then I will just use the back camera. But I can't see. Okay, so what I want you to do is I will draw what you should do now, yeah? Okay, so this is your pepper, right? So when you hold your pepper like this, when you hold your pepper on one end, what happens is on the other end it will fall down, right? Correct. Okay, so what I want you to do is when you hold your on one side, this is how the pepper will looks like, when you hold them on one side here. So your pepper will fall down like this. Okay. The red color one is your pepper. So I want you to use Bernoulli principle to raise out the pepper so that the pepper, instead of hanging down like this, it will go upwards. How do you, or how would you, oh, I'm muted, sorry. Since when did I muted? Sorry. Okay. This is your pepper. Sorry. Okay, this is your pepper, right? So when you hold them on one side like this, your pepper will hang downwards, as shown in the picture, correct? So, as an engineer, I want you to use Bernoulli principle. To use Bernoulli principle on how to move the pepper upwards. Instead of hanging down, you want to move it upwards. To this. So when you hold the pepper with your hands, and your pepper will go upwards. So how will you do this? Anyone want to demonstrate? So let's turn off the sharing. Wait, I haven't seen. Anyone wants to demonstrate? So yeah. Can we have a side view? Okay.
Yay!
Is this a magic, yeah? You see, the place where he blow the pepper is not below the pepper, but it's on top of the pepper, see? Okay, so how about others? Anyone wants to second it? Very good. How about others? Why haha? You didn't put on makeup today, right? They will only look at the pepper. Why? Because this is magic. Yes, very good. Wow, you all. I guess you all must be eating very full for your lunch. That's why you all have so much energy. Yes, correct. Huh? So, you all are very smart. Yeah. So what you have to do is, okay, without touching the pepper. Wait. Okay, sorry. I think I forgot to. Okay. Yes, huh? Without touching your pepper. Here. So I will use orange color. So without touching the pepper, you put your mouth here, okay? And forgive my back drawing. Yeah? So your mouth is here. You have to blow on top of the pepper, and what happened is the next moment magic happened. Okay, your pepper will automatically go upwards and become flat. So depends on how much strength that you that's why I said if your pepper is too large, then you can do that also, but you need a lot of strength to really blow on top of the pepper. Yeah, that's why you must eat a lot. Otherwise, right, short of breath later, then you pass out. Okay, so this is the magic. You can use this to, not to cheat lah, but to explain to young kids. See, this is Bernoulli principle. Alright, so what we want to do now is to do calculation. Okay, but too bad here because we do not have any the speed meter, something that can measure the speed. So what we do is only a prediction. So we want to predict what is the minimum speed so that we can raise out the pepper. Okay, so now back to our calculation. Something very boring, yeah. So I turn off my camera again, otherwise my computer will overheat. Okay, so when it comes to Bernoulli principle, okay, the first things that we have to do, we must choose the correct point. So for here, perhaps we choose our first point to be below the pepper and the second point above the pepper. Okay, So list down the information. So the absolute pressure at point 1, it's at atmospheric pressure. So just put down as atmospheric pressure. And the velocity, so if you are in a normal room and dry air, okay, so it's around 0.05 meter per second. And that is the information that we have. So the second point would be above the pepper, so definitely there will be a change in pressure, right? This is what we want to know. And the velocity is also what we want to know. Okay, so for this case we will just assume the elevation will be the same. Okay, because there is only a difference in a of the, how to say, a width, oh no, it's only a difference of the thickness of a piece of pepper. So y1 will just be equals to y2. Okay, so what we will do now here is we want to find what would be the minimum velocity of the wing on top of the pepper. So what can we do here is, again, look at the free body diagram again. So the mass that will cause the pepper to go down is definitely the mg, right? And there should be a force which will pull the pepper going upwards. So this force is caused by the difference in pressure. So it will be the change in pressure times the area, correct? So now we would like to find what is, okay, so find first the force, then from there we can find the change in pressure, and from the change in pressure we can determine the velocity. So I will make this so find the force first, change in pressure times area equals to mg. Given the mass of the pepper, right? Did I write down the mass of pepper? Is for my pepper is around 14 grams. So 14 convert to SI unit, which is very small only. 0.1372 Newton. The area of the pepper is, from the dimension, 0.21 times 0.05. So change in pressure between the 2 points, 13.1 Pascal. Okay, so from our Bernoulli equation, Which one do you think will gives you 13.1? Should it be P1 minus P2 or P2 minus P1? A or B? Do you need time to think? I give you 10 seconds. B or B?
B.
B. Okay, so I want you to think, which point will have higher pressure? Below or above? Let's look at this diagram. Below will have higher pressure. Okay, so below is 0.1, right? Correct? Below is 0.1. So this one is higher, this one is lower. So in order to find the difference, it will be P1 minus P2, which will give you 13.1 because P1 is larger. According to Bernoulli principle, P1 is larger, correct? So rearrange the equation here. So P1 minus P2 plus half rho V1 square. So for rho gy, we can just equals to 0 because y1 is assumed to be equals to y2. And equals to half rho V2 squared. So can you find your V2? Can, right? So P1 minus P2, 13.1 plus half. Density of the air, 1.225. V1, it's around 0.05 square, equals to half. V2 is the unknown. Not 1000, it's 1.225. What is your answer? For V2? .62, yeah. Okay, so this is the minimum 4.62. Here you have to constantly create a speed of the wing of 4.62 from here to here across this whole area. Then the whole paper will be lifted up. Okay, so if we have the chance to get a speed meter, then we can actually verify. Okay, but in fact, in real life, we won't get the exact same value again. Why? Because there are a lot of others factor which we have already ignored. Let's say again, the resistance. Okay, the viscosity, So, but the value will be more or less the same. Okay, so this is how we calculate the question like this. Okay, so like say something that related with wait okay, something that related with wing, okay, on top and below. Okay, so that it's first case scenario. And another case scenario is about like pumping the water from one container to another container. So this one, when back in campus last time, we have the chance to try out. Okay, but this one you can also try at home. So the technique here is called as siphoning, or we can say pumping the water from one container to another container. So first of all, you must create a vacuum in your pipe here. So because of the difference in pressure, the water will be pushed by the atmospheric pressure to go into the pipe, and it will continuously to pump all the water from the first container until the container is empty. All right, so for this case, what you have to do is to calculate the time interval in order to empty the tank. So in this case, usually we will choose the lower point as our point 1 and the higher point as our point 2. Okay, so point 1 is on the street, whereas point 2 is surface of the tank. So list down all the information. So at point 1, the pressure, absolute pressure at point 1 is at atmospheric pressure. It's assumed to be atmospheric pressure. Why? Because it is exposed to air. Okay, and at the same time, even though the water that come out in high velocity, but then you have to check on the, so this is what happened, yeah? When your point is lower, okay, when your point here is lower, at lower point, and when it is exposed to air, so usually we will just assume the absolute pressure at that point to be atmospheric pressure. Okay, unlike our previous example when it is all in an enclosed pipe, then that one you cannot assume as atmospheric pressure. But in this case, when it is exposed to air and when the point is much lower as compared to another point, then we can assume our absolute pressure as atmospheric pressure. Okay, so velocity 1 remains unknown, y1 here, so we set this as our reference point, which is equals to 0. Now look at point 2. So at point 2, the absolute pressure again is also equals to atmospheric pressure. Okay, on the surface it is also exposed to air. The velocity, it's assumed to be 0. So this one is always refers to the velocity of Okay, the velocity of the water flow on the surface of tank. So if you have a tank and there is a leakage at the bottom of the tank, then the velocity on top of the surface, it's assumed to be 0 because it will be very much slower as compared to the velocity of the water at the leakage point. And your Y2 now is D, which is here. Okay, so to find the time interval, in order to drain out all the water in the aquarium, in the tank, so we can actually find from our volume flow rate, right? Remember our volume flow rate, this one is equals to the volume divided by time, and also equals to A times velocity. So this is the time here. Okay, so in order to find the time, we have to know what is the velocity first. Okay, so find the velocity from Bernoulli equations. So P1 plus half rho V1 square plus rho GY1 equals to P2 plus half rho V2 square rho GY2. So plug in the value, both equals to atmospheric pressure Y1 equals to 0, V2 equals to 0 also, Y2 is replaced with D. So cancel off, 0 also cancel off. So left only half rho V1 square equals to rho GD. Simplify the equation and we get our V1 equals to 2GD root square of 2GD. Now from the volume flow rate equation, volume divided by time equals to A1 times V1. So the volume of the tank check on the question. The volume the area of the tank is A. Okay, this is your tank. Yes, what question? This is your volume. Sorry, this is your area. Accident. Are you okay? Okay, so this is your area. Area is given by A and the depth is given by H. So the volume of the aquarium will be AH. Divide by time. Okay, A1 will be the area of pipe. So based on the questions, the cross-sectional area of the pipe is A prime. So velocity 1 is what we have found just now, 2 root square of 2 GD. So rearrange your equation and you get the time equals to AH over A prime root square of 2 GD. So it's proven in your question. Right, AH over A prime root square 2 GD. So evaluate the time interval required to empty the tank. So the value is given. If the tank is a cube, okay, so this is, which means the volume now, okay, or this is the dimension 0.5. So it will be either the length, the width, and the height of the tank, 0.5 meter on each edge. And A prime is 2 centimeter square, and D is 10 meter. So plug in the value only. Okay, so part B. So AH just now is 0.5 times 0.5 times 0.5. A prime 2 centimeter square, right? So convert to SI unit times 10 to the power of -4. So 2 G 9.8. D given just now was 10 meter. So you need 44.6 seconds in order to empty the tank, right? So that is for when you have a tank and the water has to flow out from the tank below the surface, and we can use this method. So for just now, if let's say you have, especially for wind condition, the one that you have to blow the pepper, that one is for wind, okay, then you can use that method in order to solve with Bernoulli equation. So, any question?
No.
No, huh? Everyone, it's okay, right? So, yeah, I haven't posted out the challenge question on Moodle yet, no? So I will do it later. Okay, so that's all for today, and thank you for coming. Bye bye.